Hello everyone, and welcome to part 2 of Unit 4, Plane Motion. In this video, we're going to take a look at a special case of planar motion, and that is the rolling wheel. The rolling wheel is a perfect example of plane motion. It has both translation and rotation. Let's consider a wheel rolling on a flat surface with points A and B. Both points move from position 1 to position 2, as we see here by their subscripts. As we saw in the previous video, we know that motion can be divided into both translation and rotation. So we see here in the middle picture that A1 translates to A2 and B1 translates to B2, or B1 prime in this case. But we also have rotation of these 2 points, of B with respect to A. Since A is located at the center of the wheel, it does not experience any rotation. However, as B moves from B1 prime to B2, we see that it does rotate with respect to A. Let's take a look at some numerical examples to get a better understanding of how this works. We're going to start with just a wheel or a disc that's spinning in place without actually translating first. So we've seen this before. So there's our wheel, and it's spinning about the center. It has 2 points. We'll have point B, and we'll have point A up here at the top. We also know that the radius, or the distance in this case between A and B, is 0.5 meters. And last, we know that it is rotating with an angular velocity of 8 rads per second. So given all of this information, we can calculate 2 things. First, we can calculate the velocity at A. Remember that the velocity at A is going to be equal to the radius between A and B times the angular velocity of the entire disk. So we can say angular velocity of AB or angular velocity A, but just be aware that, of course, any point on that disk, it is the same angular velocity. So we can calculate that because we have half meter for a radius, we have 8 rads per second for the angular velocity. So this gives us a velocity at point A of equal to 4 meters per second. Now this is a vector, so we should know its direction. Remember that this linear velocity that we're finding is a tangential velocity, so it is tangent to the radius arm. So that tells us then that the resultant velocity should be 90 degrees to this radius arm here. So this is the velocity at point A. What we also found in part 1 was that in order to calculate an unknown velocity, we have to know, or not know, but we have to include a relative velocity term. So in the case of a disk, we have a very special case of the velocity of A with respect to B. Now remember, that's like you're positioning yourself at point B and you want to know what's happening at point A. Well, if you remember, whether you're translating or not at point B, point A will look like it's rotating about your position. And so velocity of A with respect to B is just equal to the velocity of A, which is 4 meters per second to the right. Now, what happens if we lower this wheel? Okay, it's spinning. We're just going to lower it to the ground. And we want to know what happens when it touches the ground. When A touches the ground, and we assume that there is no slippage, then right at that instant, point A appears to be stationary. However, even though that point appears to be stationary, there is still a relative velocity between A and B. And that relative velocity, again, is going to be at a right angle. And you would do the same calculation. It's going to be the radius arm times its angular velocity, which just means in this case that VB is equal to the velocity of B with respect to A instead. So again, now you're still positioning yourself. This time you're positioning yourself at A, not B. And B appears to be rotating about point A, about your position, and that's 90 degrees to that radius arm. So that would just be equal to R times omega, and since it's the same radius, for this problem, it would be 4 meters per second to the right. So let's take this even further. Let's try to actually break this up into both translation and rotation to see what the velocity would be at various points on this disk or on this wheel. So we're going to start with rotation, and we said that the top position, if this is rotating, it would have a linear velocity of 4 meters per second if this is rotating, so 4 meters per second at that point, plus it would have 4 meters per second at the bottom point, right? And really, you can pick any point on here. It's always going to be tangent to the radius arm. So we have 4 meters per second, 4 meters per second, and 4 meters per second, all at 90 degrees, or tangent to the wheel itself. That's what happens if we assume just the rotational aspect of this wheel. Now, if we just consider the translational aspect of this wheel, as we saw right up here, we know that VB is translating at 4 meters per second. And actually, we can say that at any point. So here, this is 4 meters per second. This is 4 meters. That point would be 4 meters. So would this one, and so would this one. So all of these are translating at 4 meters per second. Remember, all we're doing right now is just breaking this up into both translational and rotational components. So now what we're going to do is we're going to add up. Remember, since these are vectors, we would have to add them up vectorially. So if we took the top point, so let's actually label these. We'll say that this is 1. So 1, 2, 3, 4, and 5. And we'll do the same over here. So our 5 different positions. So we're going to take a look at position 1. They are both moving at 4 meters per second to the right. So because of the rotational component, 8 rads per second times the radius arm gives us 4 meters per second to the right. We also know that this entire wheel is translating at 4 meters per second. So what ends up happening is we add those up, we just get a total of 8 meters per second to the right at that point. So at position 1. And we're going to go around to each of the points here and add these up vectorially. So the next one would be 4 meters per second to the right, but then we have to add the 4 meters per second down, which would give us a total located in that direction. And if it's 4 meters per second and 4 meters per second, we can use the Pythagorean theorem to find that that gives us 5.7 meters per second at point 2. That would be actually similar if we skip to point 4, it would be similar, right? Because we have a value here of 4 meters per second to the right plus 4 meters per second, if we look over here, going up, Same thing except a different direction, and that is 5.7 meters per second. Now, in the last case, we have 4 meters per second going to the right and 4 meters per second going to the left. So that's at position 3. So if we add those up vectorially, we'll find that we actually get 0 meters per second at that point. So remember, we made the assumption that if there was no slippage, that point would appear stationary. And in fact, if we break this up into its components, we see that that is actually what's happening at that point. It's kind of like at that instant, it's rotating about that point. And if that's the case, then what we can do is actually draw a radius arm to any other point on this disk. So that's what I'm going to do here. So I have that point, so point 2, point 1, and then point 4. And you'll see now that when we added up those velocities, the resultant velocity is at 90 degrees to the radius arm. So this is great because now you can pick any other point on this wheel and we would be able to know the direction. So for example, I can pick something even right in the middle of this. I could go right here, say 0.6. I'm going to say right there. So what I would do then is I would draw the radius arm from 0.3 up to 0.6, and then the resultant velocity would have to be 90 degrees to that. So we would know it would be right there. And all we would have to do in order to calculate it is multiply the angular velocity times that radius arm. So let's take a look at example 12, and this is located on page 403 of your textbook. In this example, it states that there is a 0.8 meter diameter wheel that rolls to the right with an angular speed of 5 rads per second. We want to determine the velocities of points A, B, C, and D on this wheel. So let's draw that out. Okay, so here's the wheel rotating at 5 rads per second, and we wanted to determine the velocities at each of the points shown here. So as we saw in the previous example, all we really have to do is find the point of contact. If we do that, and we know the radius arms, then we should be able to calculate the magnitude of the linear velocity. So let's see if we can do that here. Clearly, this is another example of just a wheel rolling on the ground, and so we can assume that the point of contact, of course, is right down here at the bottom. We're going to call that O for our point of contact. And now what we're going to do is we will look at the radius arms for each of these points. Let's start with point velocity. Let's start with velocity at point A. So the velocity at A is equal to the radius arm from O to A. That's why you use the subscripts here to make it very clear. We're going to multiply that by the angular velocity of the wheel, which is 5 rads per second. So that is equal to, we know the radius is 0.4, so from point O to point A, that would be 0.8 meters times 5 rads per second, which gives us 4 meters per second, and it would be directly to the right since point A is directly straight up from point O. Okay, so that is the velocity at point A. Now let's take a look at the velocity at point B. So this would be VB equal to ROB equal to ROB times omega. So B would be 0.4 plus 0.2 meters. since we're going from O to C, which is 0.4, and then another 0.2 meters from C to B. So 0.4 meters plus 0.2 meters times 5 rads per second. So VB is equal to 3 meters per second, also to the right, again, because it's directly above. Similarly, we can find the velocity at point C. So the velocity at point C, the velocity of C is equal to ROC times omega, is equal to 0.4 meters times 5 rads per second, which is equal to 2 meters per second to the right. Last but not least, we have the velocity at D. And this one's just a little bit different because it's not located, point D is not located directly above the point of rotation. It's not located directly above O. So this would be VD is equal to ROD times omega. So let's go over here, and what we are doing is we are creating a rotation arm between these 2 points. So we would need to know what this R value is. Well, we know the height of that triangle is 0.4. We know the width of that triangle is 0.4. And so just using the Pythagorean theorem, we know that the radius then between those 2 points would be equal to 0.57 meters times 5 rads per second. And so VD is equal to 2.83 meters per second. Now it is a vector. We have to show the direction. Since both sides of that triangle are equal, this would be 45 degrees. So I went pretty quick. If you're unsure how I got ROD, all I did is I took the square root of 0.4 squared plus 0.4 squared. And that gives you 0.566 meters or 0.57. Okay, so let's take a look at an example at the end of the chapter. This is a really good practice problem because it's one that students do have some difficulty with. Remember, the key with these special cases with wheels is to locate the point of contact and then calculate from that radius arm. It makes sense when I say it, when you read it, but it's easy to forget that when you're actually doing these problems. So let's look at 1237. Okay, so in this problem, we want to determine the velocity at point B. We are given that we have a wheel that is rotating. There's actually 2 wheels that are rotating together, so they're bolted together at the center point here, but it's actually rolling along, that inner wheel is rolling along a ground of some sort. And we know that that inner wheel has a diameter of 0.3 meters. The external wheel has a diameter of 0.8 meters. And we know that the velocity at A is 2 meters per second. So we want to calculate the velocity at B. Now, as I've said before, you always start at the end where the information is given. Typically, this is where a velocity is given, and work our way backwards. So we can see velocity at A, which is 2 meters per second, is actually the furthest point in this diagram here to point B. So we have to work our way backwards from there. So that's why I created this intermediate point, and I named that point C, and I even indicated a velocity at point C. And the reason here is just to show you how these two are connected. We do have this wheel, so it's sort of like a double pulley system here. And so the cable that is connecting these 2 pulleys obviously have points of contact, especially at point C here. And so if the block at point A is moving down at 2 meters per second, then the point C must be going in the direction to the right at 2 meters per second. Okay, there's just no other way around. It doesn't matter what's happening to the angular velocity. Of course, it has some sort of angular velocity, but that's dependent on the fact that velocity A is 2 meters per second. So the point C, velocity at C, is moving to the right at 2 meters per second. Now from there, we should be able to work our way to velocity at B. Remember, linear velocities are not the same on wheels, but angular velocities are. And so if we can find the angular velocity from the velocity at C, then we should be able to work backwards to the velocity at B. So we'll start then by stating that VC is equal to R times omega. Now this is the key part here. What is the radius arm? A lot of people here would say that the radius arm is 0.4 meters because that's the point of rotation to point C. But this is where you would be wrong, because remember I said with wheels, since this is planar motion, we have to find the point of contact. And so the point of contact here is actually, we can create a whole other point, we'll call that point O, right? That's the point of contact for the wheel on the ground. And so the radius arm then would have to be between these 2 points. From VC should be between point C and O. And so if we want to put in our subscripts, I would say that this is ROC times omega. So we know that VC is 2 meters per second. We'll put that in. ROC would be 0.4 meters minus half of 0.3 meters, which is 0.15 meters, times omega. So then we would calculate that omega is 8 rads per second. And of course, to create that linear motion, it would need to be rotating counterclockwise, as I've shown in the diagram here. That's great. Since we now know that these wheels are rotating at 8 rads per second, now it's pretty easy to solve for VB. So VB is equal to, remember this has to be, because it's not just rotating, this is rotating and translating, so still it's ROB times omega. So that means it would be 0.4 meters plus 0.15 meters. Remember, we are going between O and B here, and then we're going to multiply that by 8 rads per second. So that's equal to then 0.55 meters times 8 rads per second, giving us a final value for VB equal to 4.4 meters per second, going to, the other thing you always have to include is the direction with vectors. So it's going to the left. So we can show that on here. So that would be VB. Why is that? Because the radius arm from O to B goes directly vertical. And so if we want to draw that in just to show that, it would go from B all the way down to O here. And they are acting 90 degrees to each other. So that would be the solution for VB.